Hello. All right. Welcome back to DSP. And most of you probably have gotten back your midterm number two. And the second midterm, unfortunately, the average is looks like about 46. 46. 44, that was in the morning. So I asked the TAs to reconsider some of the grading. So there's some of you might have gotten a new score. So now the average is 46. Okay. I'll discuss with the TA whether to shift for everybody. Yeah, I mean the course is not supposed to fail you, right? But your life is. No, I'm just kidding. I'm kidding. Life is much tougher than the course, right? Yeah, what doesn't kill you makes you stronger, right? Um, so, but I will not take the square root and multiply by 10. I don't think that's fair, because yeah, there could be a shift. Okay, it could be a shift just to encourage you that don't be too discouraged, because the high score, what is the maximum score this time? 71 only. Right, so apparently maybe the test might be a bit too tough on the tough side. The high score received before you can still argue. It's still your right to argue with the TA about your score. But right now it looks like the high score is 71, which is quite low. Okay, which is quite low. So I would consider a shift. But at the same time, I want to tell you, I look at all the different questions, right? There were 5 questions. So we look at the distribution of score for each individual questions, and we found that almost in every question there is one person who got full score. In Chinese 每一题都有满分了，几乎。The only exception are question number 1 and there's another question 4B. For 4B, I intentionally designed it so that it's really tough to get full score. That's 4B. But also for question number 1, the high score now it looks like 13, right? 13 out of 15. But otherwise, all the 3 other questions, for all the other questions, we have somebody who received full score. So that means that at least for every question, at least there exists one person. there exists one person who got the full score. So to me, that's a sign that you work hard. Okay, you all work hard to decide which question to focus on. Right there when you were doing the test. Okay, I think you should give yourself an applause for fighting on the spot, right? Given only 2 hours, right? So you should be proud of that. If you're fighting, you're good. Okay. All right. But otherwise, as I mentioned, we will. I've announced the plan for the next few weeks, and I would like to officially go through the midterm number 2, probably tomorrow, because I will go home and write down a solution, a reference solution for you to consider. So that will happen tomorrow. Okay, but otherwise today we will finish this lecture and then we enter our last topic. Our final topic would be basically FFT, the fast Fourier transform. So that will be our last topic. And at the beginning of the semester, I was a bit too ambitious about the plan. So on the schedule, I listed a few optional topics that I might consider offering, but it seems that we don't have because they're optional. Okay, so one of the topics that I truly like to discuss is adaptive filtering, 适应性的 adaptive filtering, 适应性的滤波啊。And it has something to, it's a kind of you can think of it as the predecessor, 就是前身了啊。It can be thought of as the predecessor for neural networks. 神经网络 neural networks. Okay, so I feel like that I plan to talk about it, but it seems that mainly because I had a travel schedule. We are going to the US next week. Actually, two of the TAs will go there with me. We are going to present a paper on cascade structures, surprisingly. So, yeah, on this topic, we basically made it nonlinear to simulate human hearing, related human hearing. Okay, so so these things, these structures on flowcharts, diagrams, can have some applications either for research or for industrial applications. So we want to finish our discussion on cascade, parallel, and different arrangement of how you actually implement the signal processing. Okay. So let's get back to our notes and take a look at what we had last time. So last time we were mentioning that when we have a sixth order system, for example, when we have a sixth order system like this one, BZ divided by AZ, we've seen it many times, for example, a Butterworth filter. And you can factorize both B of Z and A of Z into 3 sets of second order systems and put them in product, multiply, okay? Multiply them, so it can always be achieved that you can rearrange the poles and zeros so that you basically find the pole, find the complex conjugate, find the conjugate, put them together, and then you have a subsystem. Find another pole and find its conjugate and put them together, you have a subsystem. So we have 3 subsystems in Cascade, and each of them is a second order system. And the corresponding flow chart looks like this. Second order system, second order system, second order system. You can put them in Cascade, or there's also an option to put things in parallel, right? Same thing, still we start with a 6th order IIR system, and by this partial fractional expansion, which means that we are going to reformulate this system function into the sum of these components, into the sum. And you can apply things like complex analysis, 复分析. You can apply complex analysis, and there is a theorem called residue theorem that may help you find these coefficients, C1, C2. And at the bottom, P1, P2 are still all the poles. All the poles right there. And then after this expansion into 6 sums in 6 terms in summation, we sum them up, and then the corresponding flow will become parallel because here we have a summation. Okay, because of summation, we have a summation in the end, and that's that's the reason why we obtain a parallel structure, a parallel implementation, an equivalent implementation of the same system. Same system. Okay, so such a kind of thing, not surprisingly, in MATLAB there are functions that enable us to finish the computation. Okay, so you don't need to manually calculate the pole locations as well as or the coefficients on top. Okay? But from here, we can apply an idea that's similar to the previous page. Okay? In the previous page, we put poles in conjugate pairs, right? We find conjugate pairs and then combine them into second order systems. For here, that's also the right thing to do. Still the right thing to do. For each pole, without loss of generality, let's begin with 1 pole, P1. Then the next thing is you want to find is complex conjugate. Say the conjugate is P2. And then combine the 2 terms to form a second order system. Okay? And after that, you do the same thing for the 3rd term and the 4th term. This is first, second, right? 1跟2, C1, C2. You do the same thing for C3 and C4. combine them. Suppose that the corresponding poles are complex conjugates. And then you combine the two of them to form a second-order system. Then, in total, we expect to have one subsystem, second subsystem, and third subsystem, just like we previously, like on the previous page. But the difference is that now they are in parallel; they're not in cascade. Plus, that there is also a constant term that you may have a constant term. Okay, you might have a constant term because we are dividing B of z with A of z. Okay. We divide B of z with A of z, the quotient might be constant, right? If both of them are sixth-order polynomials, right? So when you divide the sixth-order polynomial with a sixth-order polynomial, you get a constant, right? And that constant corresponds to this term right here, okay? So in total, we have one path, second path, third. We have four paths, 四条路径, or we have 4 routes for in parallel. And when we just parallelly process the signal and then finally combine them by summation, you get the output. Okay? And this is an equivalent implementation like you can find an equivalent system like that, either in Cascade or in parallel. Yeah. Okay? So that's where we're at last time. So now, the next topic, let's switch to FR just for a few moments. Okay, all the previous plots, if you notice, we all have feedback, right? Whenever you have feedback, the impulse response is going to be infinite, and this is going to be an IIR, an infinite impulse response system, right? But now for FIR, let's take a look at this system. Okay, take a look at this system. Can you tell me what is the let's say the system function, right? Suppose that this is the input, that's the output, right? So just do a quick look. The answer is really not that hard. So this flow chart, what it does is convolution. It takes the input right here and then convolve it with H, our impulse response. And in this case, our impulse response has finitely many samples from H0 to HM, big M, the last sample. Okay, so basically, this flow chart, what it does is to take our input, so the output becomes H of n convolve with H of n, and you just explicitly, 就是很明显的啊 explicitly put H0, H1, H2 in this order, and the final sample is right there. Okay, and in each node right here, we have a branch from top and a branch from the left, right? A branch from left, branch from top. So there's always summation. We sum them all up along this path. This is a summation path. We just keep summing the different branches along this path. But on top, we have the delay line. Okay? On top, we have the delay line. So if you will, we know that right here is x of n. Right here is x of n delayed by one sample, right? So of course, this is xn minus 1. Then this is delayed by 2 samples, and so on, right? So hopefully it becomes clearer that indeed, in this structure, what we do is convolution, basically. Because we are now multiplying x of n with the first of FIR sample, the first coefficient in your FIR system, delayed by one sample, then xn minus 1, delayed by sample is multiplied by h1, and so on. So therefore, you can verify that in the end, right here we have we have x of n minus big M, and when we multiply by filter coefficients and sum them all up along this path, in the end, yn should be equal to summation what? We have a summation, okay? We have a summation from, let's say, small m from 0 to big M, we have x of m minus m times h of m, and you know that this is the convolution expression, right? You know that this is convolution. Okay, so fairly simple. This is one possible way to implement a general finite impulse response system. Okay, for any h0 to hm, as long as the impulse response is finitely long, 不会是无限长化. You can always do this. Yeah, you can always do this. And this structure has a name. This structure looks like something. Can some of you tell me that? What does it look like? A ladder. 看一下这样梯子啊. What else? It's a ladder system. Okay, yeah. It's called a ladder structure. Yeah. This is indeed, some people call it a ladder. Thank you for the guess. Yeah. Ladder structure. So there's a ladder structure in the textbook. If you want to have some extended reading in the textbook, there's another structure called lattice. So that structure looks like a 金格 or a lattice. Yeah. So just for your information, there's another thing that we are not going to cover this semester called lattice structure. But this structure, sometimes people call it the ladder structure for FIR implementation, yeah, where our samples, our filter coefficients can be arbitrary. H1, H2, all the way to the last sample. These coefficients can be arbitrary, 可以是任意的, arbitrary coefficients. So that means that for any arbitrary FIR system, we can always implement it using this ladder structure. Okay. Yeah. But the next page, I'm going to show you another structure, okay, which can simplify our computation, can reduce the computation load. But there's the criterion. Okay. So in the next slide, so any questions so far? Is this good? Yeah, ladder structure. Yeah, it's pretty easy. The next slide here looks a bit different, okay? So what's going on right here is that still we have delay line. We have a delay line right here. So here we do have x of n minus 1. That's xn delayed by one sample, xn minus 2, and so on. And there is another. The delay line continues like in this direction. Okay, delay here, and turn around, and keep delaying our signals. Okay, so that's the first thing to notice. In this structure, we have a delay line that goes around like that. That turns around in the end. Okay, so here we may have, if I understand correctly, after n minus 2, so many samples of delay we have that's part of the delay line. But then we keep delaying our signal by one more sample. Then here we have x of what? X n minus m divided by 2 minus 1. Yeah, we delay the signal further. Okay, yeah. And so on, right? And in the middle, you notice that here we sum up, okay? In these nodes, note that we have two branches flowing into the same node, so that's a summation. That's a summation right here, okay? And then finally, after summing, we multiply with filter coefficients. After summing. So what's going on here is that this is an implementation of a linear phase system. Linear phase system, okay? And the idea is that for the kind of FIR filters, let's say Kaiser design using a window, for example, the Hamming window or the Kaiser family of windows, right? So remember that we have studied this kind of filters, designed through the window method. Okay. So if you remember, what happened is that we multiply the ideal low-pass response, which is evenly symmetric function, the sinc function in time, and we multiply it with also an even a window with even symmetry. So the resulting FIR coefficients is an even function. Okay, I mean So this implementation is suitable if your filter is a evenly symmetric filter. Okay, so what's going on here is that we have the middle sample m divided by 2. Now keep the middle part, right? Remember we've been keeping the middle part, and otherwise to the left and to the right, if your filter look symmetric, like that, and the total length of the filter h of n. If your h of n has an even symmetry around time m divided by 2, okay, this is a middle sample of your filter. If this is the case, if otherwise h of m divided by 2 plus k equals to h of m divided by 2 minus k. If this happens, if this relation holds for all k, that means if your filter h of n has a middle sample, but otherwise, if you look to the left, to the right, if we look to the left or to the right, the filter coefficients have this symmetry. Then we can simplify. We can first add, then multiply. Okay. Then basically, I just need to point out that h0 equals to h of m. h1 equals to h of m minus 1. That should be clearer. Let me just write one more term. Then h2 equals to h of m minus 2, right? If we have this symmetry, if the first sample equals to last sample, in our filter coefficients, if our first sample right here equals to the last sample, the second sample equals to the second sample from the, if we count backward, and so on, third sample. If our filter has an even symmetry around time, around its middle point, okay, then what's going on here is in this implementation, we can just have a note, okay, that please realize that h0 equals to hm, okay? h1 equals to hm minus 1, and so on. So therefore, you realize that hn will be multiplied, will contribute to the output by multiplying with h0. Let me say that again. hn, the current sample, you receive a new sample, right? It contributes directly to the output by this path. Now take a look. It goes here, and it multiplies with h0, and it contributes to our output, right? And the previous sample, that's the sample we received from the previous time, right? Which is xn minus 1. It also contributes to the output by this path. It multiplies with h1, and it contributes. There's no delay. Note that there is no delay right here. Everything here is instantaneous, 瞬间的, instantaneous. Okay, so the previous sample xn minus 1 contribute to the output through this path, and along this path, you'll note that it multiplies with h1. And so far, so good. Similarly, Hn-2 contribute to the output by multiplying with H2. So this is, things look like it is an implementation of convolution, right? And all the way to the middle, if we delay the sample by n-2 samples, then it contributes to the output by multiplying with the middle sample of our filter. And then it instantaneously contributes to the output. But then what happened to, if we further delay the sample? Okay. Now, here, note that this sample right here really is x of m minus m. And this sample right here is x m minus m, plus 1. Okay, yeah. So these previous samples also contribute to the output, of course. But they contribute to the output by what? By this path. It multiplies with H0. But H0 is equal to Hm, right? So we correctly put x of m minus m right here and multiply that sample with h of m, which is the correct thing to do. And that product, 这个成绩, this product contribute to the output. So there's no violation. Still, this is a good implementation of convolution. And similarly, the sample next to it, in this sample, it contribute to the output through this path by multiplying with H1, but H1 is equal to Hm minus 1. So pay attention that this input sample is multiplied by this filter coefficient. That's the correct thing to do, right? Convolution. As long as we have an even, as long as our filter coefficients have an even symmetry, okay? If this is the criterion, if the filter you design is evenly symmetric, then we can utilize this structure, which look a bit more complicated, but the benefit is that if you just pay enough attention, you'll realize that the advantage, the 好处, the advantage of this implementation is to reduce the computation load by 50%. Why? Because we perform summation first, then multiplication. Okay? When we sum up, for example, when we sum up x of n with x n minus m, sum them up right here, and then we perform multiplication, then we just reduce the need of multiplication by half. You just combine the two terms first, then they multiply the same number, right? So why do you need to multiply them 2 times, right? How about we just use 这叫什么分配率? We just perform summation first, then multiplication. And this is a good habit. You are encouraged to have this design, to design a system like that, okay? So the key concern here really is to reduce the number it takes the number of multiplications that's necessary in order to complete this filtering process. Okay? The key motivation is really to reduce the number of multiplications. And in this structure, it looks like things are successful. Okay? All the contribution, if you take a detailed look how the samples are multiplied with filter coefficients, you realize that everything is correct. Okay, so it's a beautiful design. Okay, and what does it look like? I don't know. I don't know what it looks like. It probably doesn't have a name, but it's a beautiful implementation. Right? Summation first, then multiplication, and the computation load is therefore reduced by half. Good design. Okay, but which applies only for filters with even symmetry. If your filter doesn't satisfy, if your filter looks like exponential, if your filter is FIR, it's not evenly symmetric, and then this filter does not apply. Okay, not evenly symmetric. Yeah, not evenly symmetric. When the filter is not, in general, it's not evenly symmetric. In general, it can last from time 0 to, let's say, time m. For general FIR filters, you may not be able to implement it using this structure, because the requirement is even symmetry. Okay, so far so good. Yeah, take a closer look. You'll realize that everything is correct. Okay? Yeah, everything looks correct right here. Okay, so that's probably the only 2 pages I want to talk about FIR filter. But before we enter the next advanced topic, okay, so we will talk about quantization and stability, okay. But before we do that, there's yet another structure I found quite thought-provoking, quite interesting to introduce. Yeah, this structure has a name, a fancy name. It's called transposed direct form. Transposed, 导致的 转制的导致的 transposed direct form. And I claim to you that figure on your left and on your right, they are equivalent. Here I claim to you that they are equivalent. Okay? And you can check by following the flow. But a more interesting question is how, take a look, they are equivalent. But they are different. They are different but equivalent. How can anybody tell me what a few things that they look different? A few things. The direction, right? You notice that in the middle, in our canonical, our classical direct form too, we have nicely put the delay line in the middle. Here we also have a delay line in the middle, but they are pointing up. They're pointing upward. And also we have feed forward first, feedback right here. Okay, it looks like these are the differences. And this implementation, we claim to you that this is an equivalent system. An equivalent system. Now we call it the transposed form. 倒过来的 form. They are equivalent, but we may wonder, how do people come up with the equivalence? Is there a more general principle which is behind this design, right? How do people come up with this design? And so just in the textbook, there are a few guidelines. So it turns out that this transposed system can be obtained from the direct form on your left. Okay, how do we obtain it? There are a few steps. To design a transposed filter, step 1 is to reverse all the arrows. Okay? Sounds stupid, right? But if you do it, if you reverse all the, I need to be careful. If you reverse all the arrows, okay? If we just reverse all the arrows, up becomes down, up becomes down, left becomes right, right becomes left. If we just up becomes down, become up, right? So here, this going down becomes going up, right? So there's only one step. Well, there's no step 2. So step 2 is to turn in your homework. Step 1, reverse all the arrows. But by doing that, your input becomes output inevitably, and the output becomes input, right? Okay, so there's a step 2. Just name your output the new input, and name the input your new output. Okay, step 2, just input becomes output, becomes output. Output becomes input, naturally, because we have changed the direction of all the arrows. All the arrows. So now the new system, in the new system, the input now comes in from your right. Yeah, the output goes out to the left. Okay, and also naturally, step 2, this if I call it step 2A, and step 2B really is not a step, but to note, to pay attention that now a summation becomes branching out. Summation becomes branching, and branching becomes summation, because just simply because we change the direction of all the arrows. So I'm saying that, for example, do we have right? For example, originally, let's look at this node, right? Originally is to branch out, one input, two outputs, right? It branches out. But now after reversing all the arrow directions, now we receive, the same node now receives two inputs, and it produces one output, right? So by our convention, 根据我们的习惯, by our agreement, by our protocol, that when we have this situation, we perform summation right at the node. Okay? So the branching node becomes the summation node, and summation node, do we have an example? The summation node right here, for example, okay? So right here, let's take a focus on this node. This node received, before we changed the direction, the node received input right here and right here, right? So we have, before we change the direction, in the graph, this node received two input and produces one output, right? But now, after changing the direction, it receives one input and produces, and it copies, it branches out to two different directions, right? But otherwise, there's really just step 1. Step 2 is to say that, basically, branching out and branching in. Now the road becomes also inverted. 变成倒反过来, the rows are inverted. But otherwise, immediately you've reached the transposed direct form. You can reach the transposed direct form simply by reversing all the arrows. And now the input becomes output, the output becomes input. You can take a look, xn right here, xn right here, right? And then after that, it branches out to go through B0, B1, B2, further going in the direction of going toward in the output direction. Okay, so that's how we obtain the transposed form from any. We claim that for any network. In the textbook, there is a claim, a larger claim. Okay, in the textbook, they claim that if you have a network, you can simply do the same by changing all the direction of all the arrows, and you produce an equivalent system. It looks really strange. It sounds really strange, I agree. But that's how we just, at least in terms of how you create the transposed system, that's the way to do. Does it make sense to you? You have a network and you change the direction of all the arrows. But now the system is an equivalent system. It's kind of counterintuitive, if I ask you. If you ask me, okay, before I learn this, if I have a network and we are changing the direction of all the arrows, in terms of linear time invariant systems, still the same system. It's an equivalent system, right? I agree. I think this is counterintuitive. But when you do a detailed analysis, you'll see that they are the same system. Any comment? Does it make sense? Is it starting to make sense? Yes or no? Be honest. Thank you for being honest. Why? Why does it not make sense? 大家看啊。对啊。Okay, let me say that in Chinese first. I'll explain later. 我的直觉就说，既然把箭头倒过来，那应该是inverse system, right? Fourier transform, inverse Fourier transform, right? But in this case, so I was explaining that this is counterintuitive because at first I thought when we have a network and we change the direction of all the arrows, the result should be the inverse system because we change the direction of all the arrows. But somewhere so somehow this is, for example, we may have Fourier transform, may have inverse Fourier transform. Okay, but it turns out that this is not the case. They are equivalent. You just write down b h of z equals to what divided by what. That system function, you'll find that they are equivalent. Okay, and this is counterintuitive. I agree with you. This is doesn't make sense at first. But otherwise, this is a rather simple but surprising fact I want to introduce to you. What time do we have? So let's, in the next hour, okay, in the next hour, we are going to talk about quantization effects. Quantization effects. A bit of a recap. So near the beginning of the semester, we talked about quantization. But we talked about quantization of the signal, not the system, right? For our signal, you remember when we quantize it using, let's say, fewer and fewer bits per sample, 8 bits, 6 bits, 4 bits. Then if your file is a music file, you'll hear quantization noise. Quantization introduces noise, 四舍五入, because we are lowering our resolution, our bit resolution. So either in image or in audio, you will see or you'll hear noise. That's the quantization effect we mentioned previously. Quantization to our signals or images. And that operation introduces noise. But in this time, we're going to talk about quantizing our filter coefficients. Quantizing our filter coefficients. And we'll have an example of stability issues. Okay? Sometimes your system may become unstable simply because of quantizing all the coefficients. Okay? And there are some solutions. There are some solutions such as to, then we recommend not to implement the direct sixth order system, but to break them into subsystems. Because in second order systems, there are ways for us to make sure that our design is always stable, even after coefficient quantization. Okay, so those are the issues that we're going to touch upon for the next hour. So let's start for a few slides. Okay, so the biggest precision issue really is what I call stability non-preservation. Big words. Stability non-preservation after coefficient quantization. That means that when we have a system BZ divided by AZ, right, with all the coefficients B0 to BM, A1 to AM, all the filter coefficients, IIR, okay? Then we need to store the filter coefficients. We need to represent those coefficients using a finite number of bits, okay? In math, they are real numbers, but in computer, they need to be stored in order to multiply with our signal samples, right? So one way or another, we need to quantize those coefficients. And here might be an example of a bandpass filter on the textbook. Okay, so this is a figure from your textbook, and it talks about an ideal design in simulation. Okay, so if we don't need to quantize, or if we have a floating point representation of our numbers, then the quantization error is negligible, 可以忽略. So ideally, when we design, in this case, we have a bandpass filter with a certain ripple control. So everything looks fine with a pass band, stop band on both sides, right? One example. And we take a really close look at the pass band. This is the pass band, same example, okay? The pass band right here, that's the pass band from 0.3 pi to 0.4 pi. And sure, you see that there's actually a ripple in this design. So if you look at the magnitude, there's a ripple that is controlled like between 0.99 to 1.01, okay? So there's a ripple, you can take a look, and you can also just compute the result, the frequency response before and after quantizing the coefficients. Okay, let me say that again. We have coefficients, right? And then after in this example, after 16 bits quantization. And you can put them in cascade form or parallel form. You see that the response almost looks identical. You can hardly tell the difference, which is good, at least for this example. You can hardly tell the difference between the solid line and the dashed line, right? But sometimes we're not so lucky. Okay, sometimes we're not so lucky. So let's take a 10-minute break. When we come back, we talk about the situation when we are not lucky. Yeah.我刚刚也是迟疑了一下，对啊，是减它。可是它主要是这个，如果 H 是这个的话，那是应该是挂号，所以它出来的加。不是，这边的话，它也你这里写，这个对的，对你这里写对的，这我想还是要再多减，因为我们是一直往每 delay 一次就减更多啊。对。每 delay 会减更多啊。那所以它乘以它看起来是错的，但是我们要注意到它等于它，对，它等于，所以它乘以它就是对的。这减过来就是这不是会是 delay 最久的。delay 因为它是从这样子一直过来的，它 delay 很久，它绕一整圈，它 delay 最久。所以这里就还要减，还是要减？对，我想应该没写错。以图来看，对，呀。但数字可能就有点不直观。好。好，那这个部分应该没问题。那这个是我好奇什么时候用到？我也不知道，就是说，或者也许课本有写，我都忘了啊。然后我觉得最有趣的是说，怎么会这真的是 equivalent， 而且好像还蛮 general， 似乎还蛮 general， 在课本上面讲说，任何 network 不见得一定要是这种长得像田字形。理解。OK， 就是一个可能是一个蛮 general 的一个 theorem 在这边，关于网络理论的某一种 theory 啊，但是我不是很熟这一块，好。这边那个HN 就是任意 filter 那个 import 它那个就是我前面没有很懂为什么就是这边它就一定要就是它的那个就是 filter 它一定要是就是左右对称的，以某一个中心为基准，然后左右对称。因为它的乘法只有发生在这些地方，它所有乘法只发生在这边，那这边就已经设定好了，这就不能改了嘛，对不对？就是说这些是设定死的东西。对。那所以就是说它 delay 了，比方说最后这项，它 delay m 个 sample，suppose 如果我们看 convolution 的这个表达式的话，它应该要乘的东西是 h。所以意思是说，可以把它想成说，就是它可能一个讯号跟它做 convolution， 然后就是去戳它嘛，所以当然去戳它那个人是他可能是这个部位去戳这个点。对，好，对，对称的某。我想想，它是对称的，它 input signal 应该不用对称吧 ？input 不用，当然不用，因为 input 是一直在跑的。你要想，每次一个新的sample句，它就有个 clock， 所以全部东西都往右 shift。对，就是我刚刚想很久，就是为什么它一定要是对称，然后会戳它。对。它是就比方说，我可能用它这个点，然后去戳这个点。对。然后用这个点，然后一戳就是可能这边这个点。对。那它戳完之后，结果是一样的。结果是一样，但是因为你这两个值其实是相等的，所以他去戳它要算一次乘法，他去戳它也要算一次乘法。那我们干脆就是说，这两个既然相等，就想办法把这两个拉起，对齐以后，然后再揪一个东西去戳掉。所以应该说就是其实戳它的那个就是 H 分。对。点跟它值是一样。我就把它就是 这样就可以少算一次乘法，先加再乘会比先乘再加要好。
是之前是乘完之后再加。
因为我们每次写 convolution 看起来都是乘完再加嘛，对。
这个都是乘完再加，然后这个是我先把
两乘，对。
这个是我先把要 convolution 的那个人的那个input加完之后，然后再乘。
就是先把 input 把它导入成这样一个环。
对，然后之后再把需要乘这个点的那个人。
乘同样的东西的就把它凑在一起，先加再乘。我这是蛮聪明的，蛮难想到的，不过我觉得看起来蛮厉害的啊。
那就是我再问最后一个，就是这边，所以这个是还没有 quantize 的那个图，这个是要10 bit quantize 的那个图。那你刚刚就是说，就是好像会有一个 error， 我其实没有很懂，为什么它会影响到那个它的。
好，等一下会解释。就基本上就是真正在做时候，如果 coefficient 被 quantize 的话，那它当然它的 pole 跟 zero 都会有点飘走，已经是有些误差在这边了，那导致 pole 跟 zero 就会漂移。
所以就是。
那所以。
我希望知道可能这个系统它那个 pole 跟 zero 它可能会移动，所以它可能就会让它就是 unstable 这样。
就有这种的危险，有这种危险。这待会儿会讲这个是根本的原因是仍然是回到根与系数啊。好。 Okay. Wait, wait, wait. Wait. Hello, hello. Right. Okay. So now we are, yeah. So if you please, can you wake up? Yeah, right. Um, so we are going to talk about our last topic, that's quantization issues. I I will call this an advanced topic. Okay, yeah. So in this semester, we've been mainly deal with an assumption. We learn all the things with an assumption that we have infinite resolution in how accurate we can represent numbers 啊，就是我们对于如何表达数字这件事情啊，we've been kind of optimistic by first assuming that we don't worry about quantization effects first. But now, in the end of to end our discussion on structures, now we can finally talk a little bit about quantization and the kind of potential danger it can introduce. If you don't handle it carefully, there might be a danger that your system may become unstable. Your IR system may become unstable. FR systems are always stable. That's still true. So in what we are going to discuss next, we are going to focus on IIR systems. Sometimes the pole locations can move outside the unit circle after quantizing the coefficients. That's the issue. Okay? The issue is your poles moving to the outside of the unit circle after quantizing the coefficients. And here on the textbook, there is an example. Okay? There is an example of a 12th order system. And what exactly the system does is not that important. It is a bandpass filter, a bandpass IR filter by the name elliptic. Okay? There are such kind of systems but it's a bandpass system, and we can just after your design, you expect to, in general, we obtain a set of parameters A and B's. So this is to say, we obtain a parameter A, B so that our system really looks like is a difference equation again. Y of n equals to what? There should be a minus sign. Minus A1 y n minus 1 plus A2 y n plus 2 and so on. Okay, and we have exactly 12 terms in this example. 12th order IIR bandpass filter can be expressed by a difference equation. We've been talking about that many times now. IIR systems are difference equations. Difference equations, so the B part, we have B0, the current input, plus B1, the input delay by one sample, and so on. Plus the last one, we have B12, x of n minus 2, where your coefficients are now given to you right here. These are the coefficients that occurs right here, okay? These are your coefficients, all the fractional numbers. And you may have some tools to help you design your filters, okay? And the result of your filter can be specified by knowing all the coefficients right here. And so far, so good. Things are looking good, okay? And so when we do a careful job in design, we know that for this example, we have the poles that are marked with crosses. These are the poles. They should be all inside the unit circle. They should be all inside unit circle, even this one. Inside unit circle, we have up to, seems like we should have 6 poles right here, a 12th order system. 6 poles on the first quadrant. You know that in the complex conjugate locations, they're conjugate. we have another 6 poles in the conjugate locations. You expect that, yeah. Right? And similarly, we have zeros, yeah. Similarly, we have zeros. But zeros does not affect stability, okay? They can be inside, they can be outside, they can be even right on the unit circle, that's okay. Yeah. Zeros will not affect stability, but poles will, yeah. So in our design, we've been doing a careful job, right? So in this elliptic circle, chances are they are designed from bilinear transformation, right? Remember in bilinear transformation, we like it because it keeps the left-hand side of the S-plane to the inside of unit circle, and we like it, right? So if we begin with a stable analog prototype, we end up with a stable digital filter, right? So things are theoretically good, but now quantization of coefficients might introduce some trouble. And in this particular example, let's take a look. So in this particular example, the authors of the textbook quantized the coefficients by 16-bit representation. 16-bit representation. Okay, 2 bytes. The authors tried to use 2 bytes to represent each coefficient. Is that clear? 16 bits, right? 2 bytes. So imagine that these numbers are going to be different, okay, after quantization. And but unfortunately, after quantizing the coefficients, now you note that some of the poles move to the outside of the unit circle. Okay, this circle is a unit circle, by the way. So this is the unit circle. Okay, unit circle right here. After quantizing the coefficients, some poles, unfortunately, we have 3 poles that move to the outside, and this is bad. Now they moved to the outside. They move to the outside of the unit circle on the z-plane, real part of z, imaginary part of z, and this is bad. Okay. And there's a reason for this trouble. Might be hard to avoid, unless we are willing to make big changes. Okay, how to make those big changes? We'll talk about that. But if you think about what's going on right here, what's going on right here is that we have a 12th order polynomial a of z, right? And the roots of a of z are the poles. We have a 12th order polynomial, 12次的多项式. Okay, the roots of them. The roots of the polynomial are the poles. So even if we carefully choose, so the situation really is a of z equals to E1 plus A1 z inverse plus all the way to the highest order term right there. Okay? And its pole, the roots of a of z equals to 0. So this is a polynomial equation, right? And we know that it has 12 roots in conjugate locations. The root of a of z are the poles. P1, P2, all the way to P12 in conjugate pairs. So that's why we are seeing only 6 of them right here at the first quadrant. 在第一象限. In the first quadrant, we can see 6 of them, 6 of the poles in the first quadrant. But that's before quantization. So let's say after quantization, a tilde z now becomes still with a 1, but a1 tilde, which is slightly different from a1, only slightly. Okay, z inverse plus all the way to the highest term. Every coefficient now, if all of them are quantized, they are going to be slightly different, resulting in a slightly different A of z. Okay. And when you implement your difference equation in there, the question is, can we be sure that we still have a stable system? And the answer is not. We cannot be sure. And we desperately cannot be sure. 我们很绝望的没办法 be sure. The reason why not is because I would say, let me just simply say that it's really hard to predict how the coefficients affect the roots. Let me say that again. You have a polynomial, and it's hard to predict, just even by introducing small changes in your coefficients. The roots might move far away. That's a problem. It's hard to control how far away your pole is going to move when we change the coefficient, even just slightly. Even just slightly. You might have heard the fundamental theorem of algebra, 代数基本定理. Fundamental theorem of algebra, okay? And sure, it says that all the polynomials has a root in the complex plane. But is there a formula? Let me ask you. In second-order polynomials, there is a formula, we all know, right? If we are given a second-order polynomial quadratic equation, we know how to find the roots. Yeah. So many of you might have even memorized the formula, right? Just minus b plus or minus square root of b squared minus 4ac divided by 2a, right? So that's a formula for second-order polynomial. That's how we know we can memorize the formula and find the roots. Yeah. We know exactly, we can exactly predict how the coefficients ABC affect the root location, the roots on the complex plane. But how about third-order polynomial? Is there a formula, right? Right, yeah, there is a formula still. For third-order polynomial, there is a formula. And how about fourth-order polynomial? 四次方程式有没有多项式有没有公式解? Is there a formula? Yes, there is a formula. Very few people memorize it. It may be really complicated, but there is a formula for sure. But in somewhere, I suppose in 19th century, I might be wrong. There is a famous young French mathematician by the name of Galois. Okay. Sometimes the translation Chelowa, yeah. Galois, a French mathematician, proved that there is no such formula. There cannot be any formula to find the root for any polynomial that has an order of 5 or bigger. 5次以上, any polynomial with the order of 5 or higher, 5次以上多项方程式, has no formula. Yeah. It's impossible to have a formula. And he discovered this, he proved this. And he developed his own theory called Galois theory. This person, Galois. Galois. Lois. Whatever. Lois. He proved that there's no such formula. It doesn't exist. It cannot exist. If it does, it violates his own theory, and he proved it. Now it's referred to as the Galois theory. Okay, if you're interested, please take formal algebra from mathematics department. Okay, they will teach you how to prove it. Yeah. So that's the very reason, the core reason why we cannot predict how the poles are going to move, even if we introduce just any slight changes in your filter coefficients. The coefficient that appears in A of z, even if we just change it a little bit, even if A1 indeed is almost the same as A1 tilde, A2 is approximately A2 tilde, even if the quantization introduce just small changes in the coefficients. But their combined effect, when we put all the terms together, we have the new polynomial. Now we are in trouble. It's hard. Yeah. It's really hard. There's little you can say. 几乎没办法说什么啊。There's little you can say. You can predict how the poles are going to move, in which direction. Are they going to move inward? Are they going to move to the right, to the left, or are they going to move out? There's no systematic way to predict that other than finally finding the roots. Yeah. Right. So this is a trouble. This is a trouble. Okay. Quantization is dangerous. It's hard to predict how the poles are going to move. And if they are moved to the outside of the unit circle, we are unhappy. We have an unstable system. Our system becomes unstable. So that's the core issue. The core issue is because we cannot predict the roots, how they are going to move. So here is a suggestion. I shouldn't say a recommendation. Here we recommend, so instead of implementing our difference equation like that, so now we are going to recommend not to do this. Okay? If you have a high order system, let's say it's 12th order system like this one, do not directly implement them using basically using any direct form. Please do not implement the filter using the direct form, which corresponds directly to the difference equation. But instead, put them in cascade or in parallel. Find the cascade or parallel equivalent system. That's our recommendation. Okay? Break them into second-order subsystems. And the reason is that we know really well how to predict the pole location for second-order systems. We can control. We can have very good control. You can be confident. Once we just decompose our high-order system into subsets of second-order systems, then we are in good control of stability. So how exactly is that? How exactly does that happen? So suppose that now for so here our suggestion is to put things into cascade. Okay, so roughly. So for that 12th order system, suppose that we just put them in cascade into 6 subsystems. Each of them is a second order system with a direct form implementation like that. Like that. 6 of them. Input output like that. Okay? So now, as I said, no, I don't, wait. Going to direct form. In direct form, where do we have feedback? This is feedback feed-forward, right? So you don't need to worry about feed-forward. The feed-forward coefficients correspond to the zeros. Okay, so you don't need to worry about them. They will not cause the system to become unstable. Okay, they're fine. But for the feedback coefficients right here, for the feedback coefficients, for these coefficients, okay, so we can blow up and make a plot like this. It turns out that these coefficients for stable systems, if your system is stable, the coefficients can be expressed by 2r times cosine theta right here and minus r squared right there. You can always call your coefficients, just express your coefficients by these parameters. So this is to say that the corresponding in this flow diagram, h of z is equal to y of z divided by x of z, which is equal to 1 divided by 1. There's a minus sign, 2r cosine theta z inverse plus r squared z inverse square. All right, so far so good. So I'm claiming, I made this claim to you. I claim to you that, yeah, you may design an IR filter, an IR system which has a high order, okay, 12 or 24, even 30, right? Fine. But when we just first arrange them into the cascade form, then each subsystem would correspond to feedback coefficient, and the feedback coefficient can always be renamed. This coefficient can always be parameterized as R squared. These coefficients originally would be, it's always positive right here, if you will. If your design is a stable system, then this coefficient is always positive and is always, you can call it R squared. That's what I'm saying. I'm seriously telling you that this coefficient is always positive and we can call it R squared. So once we call this coefficient R squared, this one here can always be parameterized as R cosine theta with a minus sign right here, minus 2 times R cosine theta. And there's a reason why we parameterize the coefficients by R squared and 2R cosine theta. The reason is that in here now, the poles P1, P2 now equals to R cosine theta plus or minus J sine theta. Or they just simply equal to R E J theta, okay? And this is before quantization. So far we're still before coefficient quantization. In the next slide, we talk about quantization. But now, the good thing is that once we decompose our system into cascade of second-order subsystems, then for each subsystem, we know exactly where the poles are. We have good control. Once we see the coefficient, we almost immediately know the pole locations, and vice versa. Once you start with pole locations, you know how to calculate the corresponding filter coefficients. Okay, there's a mapping between pole locations which is R e to the plus or minus J theta. I forgot the term. Plus or minus J theta, and they correspond to this polynomial, A of z. This is our A of z. It's easy to find the correspondence between pole locations and filter coefficients in one way or in the reverse direction. Okay, it's pretty clear how they correspond to each other. So now, let's say for the first subsystem, okay? Let's say for the first subsystem we have 1 A of z equals to 1 plus A1z inverse plus A2z minus square. And B of z is also a polynomial, B0, B1z inverse plus B2 z minus square, okay? So in the next slide still, now we can be safe. We can feel all right to quantize our coefficients, okay? Once we find the second order subsystems, then we can be, we don't need to worry too much, okay? Now you can go ahead and quantize your coefficients. 1 minus 2, when A1 equals to, basically A1 equals to 2R cosine theta, right? And A2 equals to R squared. This is A1, actually with a minus sign, and this is A2. So now you can be 你可以放心啊。我今天英文I'm losing my English 啊。You can be 放心。You can have peace in your mind, okay? You can have peace when what you have is a second order system. Feel free to quantize your coefficients now. You have the blessing to quantize your coefficients now. Okay? Why? Here is a beautiful plot. Okay, let's take a look, focus on right here. Okay, so here on the right, we have the first quadrant again. Okay, and remember our A of z. So what we really quantize is A1 and A2. These are the coefficients we need to quantize. Okay, and here is an example of quantizing them using 4 bits on top, using 4 bits. So for example, if your A1 is minus point, you know how to do it. Okay, A1 is minus 0. Let's say 28. And we are going to quantize A1 with 4 bits. Right? So that goes back to our previous discussion about quantization, using two's complement scheme or whatsoever, right? Using any scheme but with 4 bits. We're going to quantize A1 with 4 bits, and the first one might be the sign bit, okay? Seriously, that's why now you have the blessing to do it, okay? 你已经被祝福了, You have the blessing to do this. This sign bit at the beginning and all the next 3 bits can be used for mantissa, right? Is it mantissa, that's the word? Yeah. So now that you feel free to quantize A1. But after quantization, maybe A1 tilde now becomes what? It seems that the nearest integer multiple of our quantization step, right? So you need to find the nearest neighbor. That's quantization, 45入嘛. Rounding it to the nearest integer multiple of your quantization step, okay? Same idea. But then we face a kind of a detail we need to decide. What's the full range? What's the full range of possible filter coefficients right here? Remember, when we quantize the signal, we need to decide the full range first. Full range, is it plus or minus 5 volts? Or what is the full range, okay? So when we ask that question, what's the full range of 2r cosine theta? What's the full range of A1? 2r cosine theta really, because we believe our system is stable, then 2r cosine theta should be between -2 and +2. That's our full range. Okay. So this is our full range, and we have 4 bits in our resolution, right? Then what is the quantization step size? That's what we need to determine. The full range is between -2 and +2. Okay. So full range for A1 is, I would say 4. From -2 to 2, right? So the full range is 4. Okay. But now we have 4 bits, right? So quantization step size delta. Our quantization, remember the notation, right? Quantization step size is equal to the full range divided by 2 to the bth power, right? 4 bits, right? So each quantization step is now, should be 0.25, it seems. 4 divided by 16, when we have only 4 bits, to quantize, to represent coefficients A1. Okay, So that's why, as I guessed, turned out that I was correct, that after quantization, A1 becomes A1 tilde, and it's the nearest integer multiple of our quantization step. Okay, that's how we need to go through. Determine the full range, and then use however many bits you have to divide the full range into equally spaced quantization steps. And then after that, we perform rounding. We round our coefficient to the nearest quantization step. Okay, is that clear? And you go through the same thing similarly for A2. Now, this is for A1. For A1. How about A2? What's the full range of A2? Now, R squared is even easier. R squared should be between 0 and 1. Because we talk about stable design, okay? In our original design, we've made effort to ensure that all the poles are inside the unit circle, right? So now, before quantization, even after we arrange them into second-order subsystems, all the pole locations before quantization, or the distances of our poles, to the origin, if we denote that by R, when we denote that by R should be less than 1. R squared should be less than 1, right? So the full range, what is the full range? Now, interestingly, the full range is from 0 to 1. The full range is from 0 to 1. So again, I may suggest for this detail, we may even want to use unsigned integer representation. Unsigned, because they're always positive. A2 is always positive when we start with a good, stable design. This A2 coefficients, R squared is always positive. Okay, so maybe I will suggest that how about we try unsigned. Okay? Unsigned integer A2 冒号啊 int 是这样子吗？All right. So seriously, that's what we're going to do. So let's say, for example, if A2 is what? Give it a number. Give a number between 0 and 1. What is A2? A random number. A2 is what? Point what? 5.3. 好. Also, can anyone tell me after quantizing with unsigned 4-bit representation, what's the result? That's the question, right? So you get the idea, okay? Delta now should be 1 divided by 16. Now it looks like that's the answer. So it seems that, what? Something like, 刚好, yeah, let's say, I might be wrong, but let's say A2 after quantization becomes 0.50. Finding the nearest quantization step, right? Finding the nearest quantization step, yeah. Okay. Right. So now you get the idea. For any second-order subsystem you begin with, right? Find the polynomial, and we know your polynomial is going to look like 1 plus. Your polynomial is going to show up right here for each of your subsystem. Okay, it's probably do the same thing for 0, but they don't affect stability, so we don't need to worry. Okay, but for the poles, do this, yeah. And just for any A1, A2, you can perform quantization. And we can do that because we know the full range. Okay, we can perform quantization. And the reason we can do that is because we know the full range. That's an important detail. So you can do the quantization. But here, this plot is really interesting in that it shows us what? All the circles on the plot show us all the possible pole locations after quantization. After quantization, now you have finitely many possible pole locations. That's interesting. I found that interesting. Okay? So, and to take a closer look, yeah, here we have like 看起来像 arcs, right? 90-degree arcs right here. We have arcs. We have a total of, it seems like there are 7 arcs. 7 arcs right here. 1, 2, 3, 4, 5, 6, 7. 7 arcs. So this plot implies that there's a total of only 7 possible radii, 半径, or radius, plural of radii. There are only 7 possible radii. And similarly, it's telling us there's also a finitely many possible real part of your pole. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, like that. 8 like that. Okay. And but can anybody tell me why this is the case? Why do we have exactly these possible pole locations? What's the reason? What's the reason? The reason is because what is A1? A1 is r cosine theta, 2 times r cosine theta. Reason. A1 equals to 2 times r cosine theta. Okay. What is r cosine theta? R cosine theta is a real part of your pole. It's 2 times the real part of your pole, P1. P1, 2. Yeah, and you know what I mean. The 2 times r cosine theta is the real part of your pole, right? And we have 4 bits. Therefore, theoretically, there should be 16 possibilities. 16 different possible values after quantization, after quantizing A1. Okay? And they are going to determine, they help us determine the real part of the pole after quantization. Is that too fast? 想一下, let's ponder on this. We want to make sure we understand this. Pretty cool stuff. We quantize A1, right? But when we quantize A1 like that, we limit, so we have limited choices for 2r cosine theta. Another way to say it, okay? We're quantizing A1, we're quantizing 2r cosine theta. And what is r cosine theta? R cosine theta is the real part of your pole, right? So therefore, and now we have 4 bits. We should have 6. You should expect to have 16 different possible real parts. The real part of your pole should be one of 16 possible choices after quantization, after quantizing the filter coefficients. Okay, so I've shown to you 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there should be another few of them that extend to the second quadrant. Okay, 在第二象限. In the second quadrant, you expect to have a few more rows. And in total, I expect we should have 16 possible values for the real part of the pole. Only 16 possible values. But it appears to me that, 16 possible values, it makes sense. 8 to the right, including 0, and maybe 7 to the left. Okay? But also when we take a look at the arcs again, these arcs. When we take a look at these arcs again, each arc corresponds to one possible value of r squared. Right? Because r squared is the other coefficient that we quantize. Okay? So after quantization, there should be only a few choices of possible values for r squared after quantization. Right? Because they are all integer multiples of quantization step. Right? So what these arcs are, the radii, if you take a look at radii, this radii is what are they? This radii looks like it's a 0.5. Okay? So it seems that we have only how many possible choices? It seems like we have 7 possible choices, at least on this plot. Of R square after quantization. Okay? So if they're quantized uniformly, then after taking the square root, right? R, what is R? The arc, the radii here really is, square root of A2. That's it. They're only correspond, the 7 possible values of R squared correspond to 7 possible values of radii, A2, okay? Actually, the 7 possible values are 0, 0.125, 0.25. 0.375 and so on. These are the possible values for R square. And when you take a square root, that becomes their spacing becomes non-uniform after taking square root. How do you quantize this R square? But what's the radii is R square is not R square but R, right? We quantize the square of radius. Therefore, the 7 possible values for R squared correspond to these several distances to the origin. That's why we are seeing these arcs at different distances from the origin. Okay, and there are only 7 of them because 1, 2, 3, 4, 5, 6, 7. There are only 7 of them, but we have 4 bits, right? So it seems that in the textbook, the author is not using unsigned representation. The authors wasted 1 bit. Okay, 浪费了. I think that they wasted 1 bit because R squared can never be negative. Or maybe I might be wrong. Can R squared be negative? When you go home, please think about it, okay? What if R squared is negative? Right, but so maybe the author, the textbook is right, okay? But apparently they are not using, they do not use unsigned representation to represent R squared, okay? Apparently. Any questions so far? Any question right here? Is it okay? Quantization now, because so to take a look, compared to 6th order or high order, 12th order system, what's cool right here? What is cool right here? What's cool right here is that we know exactly where the poles are after quantization. That's the message. Okay. And the reason is because we simply have a 2nd order system. We have a formula. We know that the pose is going to be occur at r times cosine theta plus or minus j sine theta. Because of this formula, we can be sure about where exactly we expect to have poles. After quantization, the set of all possible pole locations become finite, a finite set. And we know exactly where they are. The poles can only occur at the intersection of all the real parts, possible real parts here, and all the radii right there. These are the places of all the possible pole locations. Okay, so take a look. That's probably the kind of important message I want to deliver today. 好吗？可以吗？ All right. And for sure, that even after quantization, even after we do this, even after we change the coefficients from minus 0.28 to 0.25, even after we change the coefficient from here to here, we can now be sure that, the pole location is going to move. Your filter response is not going to be as good as you hope it to be, but just to say the least, we can be sure, we can have peace in mind that at least our system, after quantization, is still a stable system. Because the pole, all these pole locations are still inside the unit circle. Because when we quantize R square, we make sure that it does not exceed 1. 它不会超过1嘛, right? When R squared does not exceed 1, we can be sure. We can be peaceful, we can go home and say our system will always be stable, even after quantizing the coefficients, okay? And you can say so just only for second order systems. We do not recommend, there's no hope if you insist to implement your system using the direct form for high order systems, okay? So that's the message, okay? And before we leave for today, take a look at this. Yeah. So now this is the same thing but with 7-bit resolution, okay? And each dot is one possible pole location. Take a close look, yeah, if you have downloaded it. Yeah. Take a close look. What can you see? What do you see? Aliasing. There's a beautiful pattern right here, okay? A beautiful pattern right here. But it seems that the density, how about the density, the distribution, is not uniform, right? We have more possible locations up when we go up, but down here, we may have not enough places to represent our poles. And so some people thought about this. Some people thought about this and they think that this might not be good, okay? We don't want the possible pole locations to have uneven to have a non-uniform distribution on the plane. That's not preferred, okay? So some people thought about this and came up with yet another structure. Yeah, smart people. Some people came up with this structure. So I'll leave it to the exercise. This will be an exercise, okay? Since that it turns out that if your input is right here, xn, yn to the output, and if we just have a branch out and feedback with a coefficient r cosine theta, r sine theta, and so on, a rather complicated form which has a name is called coupled form. When we just, it turns out that this system has the same pole location as this. Since that the pole location, as we know, is r times e to the plus or minus j theta. So that's for sure for this system. We understand it really well. But it turns out that this system also has the same poles. They have different zeros, but it turns out that this coupled form also has same poles. Smart people. And further, now, miraculously, the pole distribution, the distribution of possible pole locations become uniform. Because like checkerboard, 变成像棋盘一样了, becomes like checkerboard, right? And even if we increase the number of bits to 7, now everything becomes uniform, and this is good. This is not so good, okay? So we'll leave it as an exercise for you to verify that these two systems have the same pole locations. So, but one final thing I want to say is that everything comes with a cost. Now we have the advantage of the coupled form has an advantage, a nice property that is pole locations can be distributed uniformly on the plane, right? That's a good thing. But at the expense, there's an expense. 代价, there's an expense of higher computation load. Did you notice? If you notice, the computation load right here is 2 multiplications per sample. But the computation load right here is 1, 2, 3, 4, 4 multiplications per sample, okay? When you process one sample, each sample, it costs you 4 multiplications. It takes four multiplications, and so that's the cost of wanting to have this nice property, okay? So everything comes with the cost. So with that, I'd like to thank you for being here. And tomorrow, let's begin with a kind of a discussion on the midterm, okay? And then will not have a discussion session. Discussion session will happen next week, okay? All right, thanks for being here. Class dismissed. 可以，对，都可以啊。